The Permian Triassic extinction occurred about 252 million years ago and ranks as the most severe loss of biodiversity in Earth's history. Approximately 90% of marine species and 70% of terrestrial vertebrates disappeared. The leading cause appears to have been extensive volcanic eruptions in the Siberian Traps region. For over roughly 1 million years, lava flows blanketed more than 2 million square kilometers. These eruptions released massive amounts of carbon dioxide and sulfur dioxide into the atmosphere, driving rapid global warming and widespread acid rain. Surface temperatures climbed by as much as 10 degrees Celsius. Warmer air retained more moisture, leading to intense storms and increased acid deposition. Acidic seawater impaired the ability of marine organisms to build calcium carbonate shells. Oxygen declined in warmer water, contributing to widespread marine anoxia. Geologists study ancient rocks for clues to this crisis. Unusual ratios of carbon isotopes in sediment layers showcase sudden injections of volcanic carbon. Spikes in mercury content record the timing of eruptions. Evidence also suggests methane release from frozen sediments on the seafloor added to greenhouse warming. Fossils, mineral analysis, and computer climate models combine to show how these factors work together to push the ecosystem past their limits. On land, forests collapsed as tree species failed to adapt to extreme climate swings. Fossil records display a sharp rise in charcoal deposits, which serves as evidence of massive wildfires. Herbivores lost critical food sources, triggering rapid declines in predator populations. Even insects suffered due to a sudden drop in amber-preserving specimens. The combined stresses overwhelmed ecosystems, causing mass extinctions. Ecosystem recovery was exceptionally slow, requiring roughly 10 million years for biodiversity to return to pre-extinction levels. Early Triassic environments were dominated by disaster taxa, a generalist species tolerant of harsh conditions. Ferns and other spore-producing plants formed sparse fern spikes, exploiting nutrient-poor soil. Small reptile groups diversified to occupy empty ecological roles, paving the way for archosaurs, including early dinosaurs and crocodilian ancestors, to rise in prominence. About 66 million years ago, an asteroid roughly 10 kilometers across struck Earth near the present-day Yucatan Peninsula, forming the Chicxulub crater. The collision released energy estimated at several billion times that of the Hiroshima bomb. Upon impact, rocks vaporized instantly, and a massive cloud of debris traveled around the globe. Temperatures at ground zero likely exceeded several thousand degrees Celsius for a brief moment. Within hours, sunlight became obscured as dust filled the stratosphere. Surface temperatures fell dramatically, initiating an impact winter that may have lasted for months. When sunlight dimmed, most photosynthetic organisms were unable to produce food. As primary producers collapsed, herbivore dinosaurs and large marine reptiles experienced rapid starvation, followed by declines in carnivorous species dependent on them. Sulfur compounds released from vaporized sulfide rocks amplified environmental stress. Sulfuric acid generated acid rain with pH values as low as 2 to 3 in some regions. Acidified lakes and rivers lost fish, and acidic soils hindered plant regeneration. Wildfires ignited globally when superheated debris re-entered the atmosphere. The temperature swing from impact winter to greenhouse warming added further strain on surviving species. Ecosystem recovery proceeded over hundreds of thousands of years. Pioneer plants such as ferns and mosses recolonized devastated landscapes. In shallow marine environments, microbial mats and small invertebrates dominated initial communities. Within 2 to 3 million years, flowering plants emerged in forests, modern coral reefs were formed, and sharks resembling today's species appeared. Simulation of ocean acidification and temperature collapse matches extinction patterns evident in fossil records. The Chicxulub event emphasizes how a single catastrophic impact can abruptly reset evolutionary trajectories, demonstrating Earth's vulnerability to outer space threats. 720 million years ago, Earth froze over in at least 2 extreme glacial periods often called Snowball Earth. Geological clues show that ice sheets covered continents and sea ice stretched into tropical zones. In some places, ice reached 1 kilometer thick, sealing off the ocean from the air above. These global freezes began when carbon dioxide levels in the air dropped too low. Continents sat near the equator where heavy rain and warm temperatures made rock break down faster. This process pulled CO2 out of the atmosphere and locked it away in sediments. With less greenhouse gas in the air, temperatures fell and ice started forming at the poles. As ice sheets grew, they reflected more sunlight back into space and cooled the planet even more. Life under all that ice faced a struggle. Without enough sunlight, ocean plants called phytoplankton could not make food or oxygen. Most creatures that depended on them nearly died out. On land, complex plants and animals had not yet evolved. Only simple life could survive in tiny pockets of open water or meltwater channels beneath the ice. Microbial mats, thin layers of bacteria, grew around vents where hot water bubbled up, creating small oases of life. Volcanoes under the ice kept releasing carbon dioxide. With weathering slowed by the ice cover, CO2 built up in the atmosphere over millions of years. Eventually, greenhouse warming overcame the high reflectivity of the ice. Temperatures rose, ice began to melt, and dark ocean water absorbed even more sunlight, speeding up the thaw. This rapid melting left behind thick layers of carbonate rock called cap carbonates, which record the sudden change from icehouse to greenhouse conditions. When the ice disappeared, rivers carried fresh nutrients into the oceans. This nutrient boost sparked a burst of new life. Snowball Earth shows how our planet's climate system can swing between extremes and how life can endure even the coldest global freeze. Roughly 2.4 billion years ago, Earth's atmosphere underwent a radical change known as the Great Oxidation Event. Before this shift, oxygen levels were almost zero. Most life was single-celled and breathed substances other than oxygen. Tiny organisms called cyanobacteria began producing oxygen through photosynthesis. Over millions of years, their activity built up enough oxygen to transform the air and oceans. As oxygen levels rose, iron that dissolved in seawater reacted with free oxygen and settled out as rust-colored rock layers banded iron formations. These formations, now visible in ancient rock outcrops, record the gradual increase of atmospheric oxygen. Once iron in the oceans was used up, oxygen began to accumulate in the air. The arrival of oxygen had dramatic consequences. Many organisms that cannot tolerate oxygen died off or were forced into isolated environments. This mass die-off opened ecological space for new life forms that used oxygen to extract more energy from food. Aerobic respiration powered the evolution of more complex cells and eventually multicellular life. Rising oxygen also affected Earth's climate. Methane, a potent greenhouse gas, reacted with oxygen and converted into carbon dioxide. Because carbon dioxide traps less heat than methane, global temperatures cooled. Geological evidence points to at least one ice age around this time, possibly triggered by this drop in atmospheric methane. By the end of the Great Oxidation Event, oxygen levels had risen to about 1% of modern levels. That was enough to pave the way for eukaryotes, cells with internal structures like nuclei, to emerge. These new cells eventually formed algae, fungi, plants, and animals. Oxygen also led to the formation of the ozone layer, which filtered harmful ultraviolet radiation and made shallow coastal waters more habitable. The Great Oxidation Event shows how a single metabolic innovation, photosynthesis, can reshape an entire planet. It highlights the connection between life and environment, demonstrating that biological processes can drive global change and set the stage for future evolutionary leaps. About 74,000 years ago, a volcano on the island of Sumatra in present-day Indonesia produced one of the largest eruptions in the last 2 million years. Known as the Toba Supereruption, it ejected roughly 2,800 cubic kilometers of ash and volcanic material into the atmosphere. This event left behind a massive caldera, now filled by Lake Toba. The eruption ejected huge clouds of ash and sulfur gases high into the atmosphere. Sunlight was blocked for several years, causing a volcanic winter. Average global temperatures may have dropped by 5 to 10 degrees Celsius. Ashfall blanketed much of South Asia, making plant growth nearly impossible and disrupting food chains. Some researchers propose that this sudden climate stress created a genetic bottleneck in human populations. DNA studies suggest that humanity's numbers may have fallen to a few thousand breeding individuals. Harsh conditions would have made hunting and gathering far more difficult. bands of early humans likely migrated to find reliable water and plant or animal resources. Other evidence, however, indicates that human groups survived in multiple refuges. Coastal areas and regions less affected by ashfall provided milder climates and access to marine foods. Animal species such as elephants, deer, and more also persisted, offering food sources for humans. Volcanic gases from Toba, including sulfur dioxide, combined with ash to produce acid rain. This rain altered soil chemistry and freshwater ecosystems for years. But within a few centuries, weathering and natural processes cleared most of the ash. Forests and grasslands slowly recovered, and animals and human populations rebounded. The Toba supereruption stands as a reminder that Earth's volcanic forces can rapidly alter climate and ecosystems. About 56 million years ago, Earth experienced a sudden surge in global temperatures known as the Paleocene-Eocene thermal maximum. For a few 100,000 years, average surface temperatures rose by 5 to 8 degrees Celsius. This rapid warming came from a massive release of carbon dioxide into the atmosphere and oceans. Scientists point to large deposits of methane frozen under the sea floor and in permafrost. As ocean waters warmed, these methane hydrates became unstable and released methane gas. Volcanic activity may have added more carbon dioxide and methane to the mix. Ocean chemistry shifted dramatically. Acidification from extra carbon weakened shells of tiny organisms called foraminifera. Deep-sea sediment layers showed a sharp change in carbon-13 isotope ratios, resulting in the rapid injection of light carbon from methane or volcanic sources. Many marine species suffered population declines, but overall extinction rates remained low compared to other mass extinction events. On land, warmer and wetter conditions expanded tropical forests towards higher latitudes. Fossilized soil layers and plant pollen revealed rainforests growing in regions that are now temperate. Elevated carbon dioxide helped plants grow faster, but extreme heat and humidity stressed many ecosystems. Signs of drought appeared in sediments from inland basins, suggesting that rainfall patterns became more erratic. Recovery from the thermal maximum took about 100,000 years, as weathering of rocks consumed excess carbon dioxide and as methane converted to carbon dioxide and then dissolved in oceans, greenhouse forcing gradually declined. Ocean circulation patterns adjusted, restoring oxygen levels to deeper waters. Marine organisms with rapid regeneration times, such as plankton, evolved new adaptations to acidified conditions. Forest compositions also shifted, favoring plant groups better suited to higher temperatures. A supernova occurs when a massive star runs out of fuel and collapses under its own gravity, then rebounds in a tremendous explosion. If a supernova happened within about 50 light-years of Earth, a burst of high-energy radiation and cosmic rays could reach our planet and affect the atmosphere. Evidence for past nearby supernova appears in deep-sea ferromanganese crusts that contain trace amounts of iron-60, a radioactive isotope created in supernova. Detection of iron-60 deposits dating to around 2.6 million years ago suggests that Earth encountered debris from one or more supernova explosions at that time. This period coincides with minor climactic shifts, though definitive links to extinction events remain under investigation. With that being said, intense ultraviolet and X-ray radiation would ionize the upper atmosphere, depleting ozone that protects life from harmful solar ultraviolet rays. Models suggest that a nearby supernova might reduce stratospheric ozone by as much as 50% for decades. Increased ultraviolet exposure at Earth's surface would raise mutation rates in plants and animals and damage marine phytoplankton, which form the base of ocean food chains. Cosmic rays from the explosion would collide with nitrogen and oxygen in the atmosphere, producing nitrogen oxides that further destroy ozone. These particles would also increase background radiation at ground level, potentially elevating cancer risk for organisms. Freshwater and marine ecosystems could face stress from both higher radiation and changes in nutrient cycles driven by atmospheric chemistry changes. Recovery of ozone levels would depend on the rate at which ultraviolet-driven chemical reactions produce new ozone molecules. Full restoration might take a few decades to a century after radioactive decay and particle influx subsides. Life on land and in the ocean would likely rebound if the supernova were not close enough to cause catastrophic damage. A supernova radiation burst shows that threats to life can come from even outside our solar system. Earth's magnetic field reverses polarity at irregular intervals, with north and south magnetic poles swapping places. These geomagnetic reversals happen over thousands of years. During a flip, the field weakens, letting more cosmic rays and solar radiation reach the surface and upper atmosphere. A weaker magnetic field allows higher levels of charged particles to enter Earth's atmosphere. Increased ionization in the upper atmosphere can alter chemical reactions, potentially depleting ozone and changing climate patterns. Elevated radiation levels at ground level would raise mutation rates in living organisms. Animals that rely on magnetic navigation, such as birds and sea turtles, might become disoriented until the field stabilizes. Sediments and lava flows record past reversals. The most recent full reversal, the Brunhas-Medeyuma event, occurred about 780,000 years ago. Geologists examine magnetic minerals in rock layers to track field strength and direction through time. Evidence shows that field strength can drop to as little as 10% of its normal intensity during a reversal, then recover in a few thousand years. Life on Earth has persisted through dozens of reversals. Microbial life in high radiation refuges like deep sea vents and underground habitats would have avoided most effects. Surface organisms experienced increased mutation rates, which drove evolutionary change. Geomagnetic reversals also affect technical systems. In modern times, a weakened field would expose satellites and power grids to more charged particles, increasing the risk of electronic malfunctions. Radiation exposure for high-altitude flights and astronauts would rise, demanding improved shielding. A geomagnetic reversal showcases the dynamic processes within Earth's core that influence surface conditions. Studying past reversals helps us prepare for future field changes and understand their potential impact on life and technology. Since the development of nuclear weapons in the mid-20th century, there have been several incidents when humanity came close to accidental or unintended detonations. These near misses highlight how technical errors, miscommunication, or human judgment under stress can bring the world to the brink of catastrophe. Nuclear weapons release energy through nuclear fission or fusion reactions. Fission weapons split heavy atoms like uranium-235 or plutonium-239, releasing energy measured in kilotons of TNT equivalent. Fusion weapons use fission to trigger fusion of light atoms such as deuterium and tritium, yielding energy in the megaton range. A 15-kiloton bomb like the one dropped on Hiroshima destroyed almost everything within 1 kilometer. Intense heat produced firestorms and caused severe burns up to 2 kilometers away. A shockwave shattered buildings and threw debris at high speeds. Prompt radiation near ground zero would kill exposed people in seconds. Fallout carried radioactive particles downwind, contaminating soil and water for years. In October 1962, during the Cuban Missile Crisis, U.S. radar falsely detected incoming Soviet missiles. Tensions soared as military leaders prepared nuclear forces. Fortunately, confirmation from additional radar and visual sightings averted a launch. That incident showed how reliance on a single data source can nearly trigger disaster. On November 9, 1979, a training tape error caused Strategic Air Command commuters to simulate a large-scale Soviet attack. Operators received a stream of false alerts. Senior officers questioned the data and realized it was a drill tape mistakenly loaded into the live system. Human skepticism and cross-checks prevented a retaliatory launch. In 1983, Soviet officer Stanislav Petrov faced a false alarm from the Oko early warning system that reported multiple U.S. missiles headed towards the USSR. Petrov judged the warnings unlikely and chose not to report them as a confirmed attack. His decision prevented an automated Soviet response that could have led to nuclear war. More recently, computer glitches and human error have continued to pose risks. In 1995, a Norwegian scientific rocket launched from Andoya was mistaken by Russian radar for a U.S. submarine-launched missile. Russian forces went to high alert before realizing the rocket's profile. Communication protocols helped avoid escalation. These near misses share common themes. Early warning systems rely on complex technology that can fail or misinterpret data. Standard operating procedures and communication between military and civilian leaders play a crucial role in preventing rash decisions. Thank you for watching this video. If you enjoyed, please leave a like and subscribe, and let me know in the comments if you would like to see more videos like this one. Thanks again. Goodbye.